Hey PStat, welcome to section 6.3 in chapter 6 on random variables. We're going to look at a couple of special ones that come up an awful lot, and these are binomial and geometric random variables. So by the end of this section, you should be able to determine whether the conditions for a binomial setting are met, calculate and interpret probabilities involving binomial distributions, calculate and interpret the mean and standard deviation of a binomial random variable and interpret those values, and when appropriate, use normal approximation to the binomial distribution to calculate probabilities. We'll kind of briefly touch on that, and find probabilities involving geometric random variables. So first of all, we need to know when we're dealing with a binomial setting. So a binomial distribution is appropriate, that you should be doing binomial calculations. And so this setting arises when we perform n independent trials, some fixed number of independent trials of the same chance process, and count the number of times that a particular outcome that we refer to as success occurs. The four conditions for a binomial setting are, they've got this set of questions you can ask yourself. Binary. Are the possible outcomes from each trial classified as like two possibilities, like binary, success and failure? All right, so flipping a coin is your kind of most classic example of a binomial setting. Are the trials independent? That is, knowing the outcome of one trial must not tell us about the outcome of any other trial. So flipping coins is great. Drawing cards, not necessarily, right, if you're not shuffling them back in. So each of those is binary when you're drawing cards, but they're not independent. So binary, independent. The number of trials, n, of the chance process must be fixed in advance. All right, that one's they call it number. That's a little forced because they're making an acronym out of this. And then same probability. And that kind of goes with independence, but it can go with other things too. But we're dealing with the constant probability over and over and over again. The same probability of success. We'll call that P. And so this is what they do. The circled letters give you a helpful way to remember conditions for a binomial setting. Just check the bins. So if that helps you, is it binary, two outcomes? Is it independent? Do we have a fixed number? And then are we dealing with the same probability? So let's look at a problem with this. Determine whether the given scenario describes a binomial setting. Justify your answer. All right, so genetics says that the genes children receive from their parents are independent from one child to another. So independent is good. Each child of a particular set of parents has a probability of 0.25 of having type O blood. Suppose these parents have 5 children. Count the number of children with type O blood. So are we dealing with the binomial setting? So check the bins. Is it binary? Success, they have type O blood. Failure, they don't have type O blood. Each of the 5, that's a little weird the way they're phrasing it. So yeah, each has, whether for each individual is a success or failure. Independent, we already told that it was independent. Knowing one child's does not help affect the other. We have a fixed number and we have a constant probability. That is a binomial setting. What about this example? Shuffle a standard deck of 52 playing cards. Turn over the first 10 cards one at a time. Record the number of aces you observe. So does it fall into the bins? Binary, yes. Success, failure, you get an ace or you don't get an ace. Are they independent? No. If we draw, the first card we draw is an ace, the next card is less likely. And if the first one's not an ace, then the next one is slightly more likely. So this is not a binomial setting because the independent condition hasn't been met. It's also not a constant probability, right? That's another thing. You can technically have independent things like, a coin flip from a die roll. Those are independent, but not a constant probability. So that's why they kind of both. But a lot of times those two go together. And then the fixed number, yeah, we did say we're going to fix a number, but we already broke our rule of independence. All right, shuffle a deck of cards, turn over the top card, put the card back in the deck, and shuffle again. Repeat this process until you get an ace. Count the number of cards you had to turn over. So we're putting it back in and shuffling. That should make it independent, right? Well, yes, but so binary, we're either getting an ace or not. They are independent now because we are shuffling. We're replacing the cards and shuffling. But do we have a fixed number of trials? Now they changed what they're asking for. We count the number of cards until we turned over an ace. So it's not fixed in advance. We're doing it for some indeterminate amount of time, and we're interested in just the one success. Usually we're interested in, out of a fixed number of trials, how many successes. This actually is a geometric setting, which is the second half of this chapter. So we'll come back to this, but that is not a binomial setting. So the blood type scenario in part A of this example is a binomial setting. If we let x equal the number of children with type O blood, then x is a binomial random variable. Remember, random variable, it's the numerical outcome, and so we're interested in here the number of people with type O. So the probability distribution of x is called a binomial distribution. The count of successes in a binomial distribution is a binomial random variable. So the possible values for x are from 0 to n. In that case, it was 5, but 0, 1, 2. So you can have 0 successes, 1 successes, 2, all the way up to n, all the successes. The probability distribution of x is a binomial distribution. Any binomial distribution is completely specified by two numbers. It's kind of similar, kind of mean and standard deviation for like some mean and standard deviation for a normal distribution. But in this case, it's n, the number of trials, and p, that constant probability of success. If we know we're dealing with that, all I need to know is how many trials, what's the probability of success, and that completely defines all I need. I can get every single binomial probability from those couple of things. Yeah, we'll do problems with once we know those two numbers. So each child of a particular set of parents has a probability of 0.25 of having type O blood, and suppose the parents have 5 children. So there are two parameters there. We've got our n and we've got our p, our probability and our number. So what is the probability that exactly one of the children has type O blood? So we kind of already crept into this a little bit before, but we can think about we're going to have 1 success and 4 failures, right? And I guess I should say now, keep in mind this chapter that success and failure, it doesn't always mean good and bad, right? Like I'll be interested in whether or not something breaks, and we'll call it success when it breaks. So success doesn't really imply it's a good thing. It implies we're observing whatever the characteristic is, the outcome that is that we're interested in observing. So doesn't necessarily mean it's a good thing. All right, so in this case, yeah, we could have 1 success and 4 failures, but there are 5 different ways that can happen. All right, so the probability that x equals 1, x is the number of successes, and so that's exactly 1 child has type O blood. And so here's a probability we could do. 5 is the number of ways to get 1 child out of 5 with type O blood. I could have the first kid get it and the next 4 don't. I could have the second kid be the one that gets it. I could have the third kid be the one that gets it, and so on. So there are 5 different ways, and then there's my 1 success, so 1 child with type O blood, and then there's my 4 failures, my 4 without. And so that gives us our probability calculation with this. So ultimately our formula, we're going to kind of adapt from this, is going to look something like this. The probability that x equals k, so k is just some number, so x is however many successes we observe, in this case k was 1, is equal to the number of ways to get k successes in n trials. That's a little bit of a trickier thing we're going to come back into, multiplied by the probability of success to k, the number of successes, and then the probability of failure to n minus k, the number minus the number of successes gives us the number of failures. So this is the probability of failure to the number of failures. Probability of failure, 4 failures. Probability of success, 1 success. And so we could adjust that. But then, yeah, this 5 number, kind of easy when we're dealing with 1. But what if we're dealing with other numbers? What if we have 2? How many different ways are there to get 2 successes out of 5 tries? How many ways are there to get 3? All right, well, that we need something new. And so we're going to be using what we call the binomial coefficient. This is also known as a combination. Now, this notation might be different than what you guys are used to if you've seen permutations and combinations before. But you really don't need to understand this. This bit is optional to understand. I think it's a good idea, but we're not going to really go into enough depth that I'm going to expect you to understand this. But if you've done it before, you should. So the number of ways to arrange k successes among n trials is given by this binomial coefficient. So this little n over k thing is a weird way of a notation of saying n choose k, right? If we're doing like a combination, and how many ways to have k successes out of n tries. So the part of the way that it works, like this n over n minus k, it's basically like if you're picking options, so say you're like 10 and you're choosing 3 of them, there are 10 choices for your first, and then there are 3 choices for your next, or sorry, 9 choices for your next, and then 8 choices, and then but you don't do 7 and below. So that's what this does. It actually cancels out like the 7 and below in that case. And then if I don't care what order they get chosen in, I actually can divide that by the number of different arrangements of those 3 things I chose. And so that's what's going on in this formula. Like I said, I'm not going to go into it in a lot of detail. It's something that's, I think, worth looking at, but I'm not going to expect you to know that. So this is, these are factorials, and you multiply all the way down to 1. And note that 0 factorial is 1. That is kind of a weird property of it. And also note that this has nothing to do with n over k. This is not a fraction. It's a way of writing that combination. There's a way to do this in your calculator. It's under probability, math probability, and it's like NCR, where it's choose R, and they'll show that in a moment as well. All right, so ultimately the formula for a binomial probability, and this is on your formula sheet right here, is that big thing right there. This is not on your formula sheet though. It does not. That's nowhere on there. They don't ever say how to do that combination. So if you can at least write those numbers in that spot, and I'll show you another calculator way of doing this, then you'll be able to do everything you need to do for the AP Statistics class. So this is the number of ways to get exactly k successes out of n tries, the probability of success to the number of successes, probability of failure to the number of failures, and that's the way this works out. So doing one of those calculations, so genetics say that, this is the same thing. We got the 25% chance that they're going to get type O blood. So we got the 5 children. Let X be the number of children with type O blood, and find the probability that X equals 3. What is the probability that we get exactly 3 out of 5 children with type O blood? All right, so we've got X is a binomial random variable with 5 trials and a 25% chance of success. And so the way that we can do this calculation is right there. You can write it, you type the formula in like that. 5 choose 3, that's a combination. That's how many ways this can be done. How many different ways can I pick 3 from 5? And then it turns out it's actually 10, by the way. And then the probability of success, 25% 3 times, 75% 2 times, and that ultimately multiplies out to be it. Here's how this can actually be done in your calculator. If you do the math probability and then you do 5 choose 3, it shows you the 10 possibilities and does it as a factorial. Ultimately, though, there's another way of doing this. You don't need to be able to type it in like this even. If you can recognize that formula, though, that would be a really good spot to be, especially since you are given that formula on the formula sheet. So there's about, once you calculate all this out, an 8% chance that you'll get exactly 3 out of 5 that have type O blood. All right, and then this preceding example tells us that each child of a particular parent has a 0.25 probability of having blood. Suppose that they have 5 children. Should the parents be surprised if more than 3 of their children have type O blood? Calculate the appropriate probability and support your answer. So this time we're not interested in exactly 3, we're interested in more than 3, which would include the results 4 or 5. And so this is what this will look like. A little bit different. We've got the outcome for 4, and then we've got the outcome for 5. And so we can calculate those individual probabilities separately. This one, sorry, should have a different number there. So this should be 5 choose 5, which is, there's only one way to get 5 successes out of 5 tries. And this should just be 0.25 to the 5th, and then that to the 0, which is 1. So yeah, that got screwed up. This ultimately all just works out to be 0.25 to the 5th. Which you guys actually already knew before the binomial calculations, how to calculate what's the probability that all of them have type O blood. So those two numbers add up, and that gives you overall a probability of about a 1.5% chance of having more than 3 children with type O blood. And so yeah, they'd be surprised, definitely be surprised. That's pretty unlikely. All right, why, so this would be good to recognize, definitely on a multiple choice, again, that with the mistakes there withstanding. But you can do this stuff in the calculator. And so I want to make sure that you see how that is done. So to compute these binomial probabilities in the TI-83 or 84 calculator, so what you're going to go to do is you're going to go to distribution. So second distribution, And so remember, normal CDF, there's normal PDF and so on in there. You're going to ultimately find a few commands that we're going to need for this. And that's binom PDF and binom CDF. They're way on down there in distribution at the bottom. In fact, if you tap up, you get to them a little bit faster. But you'll find binom PDF and binom CDF under second distribution, the same spot where you find normal CDF. So to compute those probabilities, you'll go in for PDF. This finds the probability that you equal something. So it's a probability distribution function. It's for equals. So if you want to find the probability that you get 3 successes when you have 5 trials and a 25% chance of success, you can just type in just like this. It'll set that up. It'll ask you for X, N, and P. And so there's their N, P, and X in that order. Sorry, I got out of order there. So N, P, and then X. And so that's the number of trials, the probability of success, and the number of successes. And it just calculates it. All right, and that number will match what we saw on a few slides back. That's binom PDF. If you tap over to binom CDF, that's cumulative distribution function. What it does is less than or equal to. And so less than or it's cumulative up to that point and including that point, less than or equal to. So if you want to do greater than 3, what we want to realize is that's the complement of less than or equal to 3. So what I can do is calculate a binom CDF with 3 or below, and then if I do 1 minus that, that'll give me greater than 3. And so you just got to do a little thinking through that. If you want to go above a number, and so what do you want to subtract away? You want to subtract away everything else. So that's what this CDF command does. And so if you type this in, binom CDF with 5 trials, 25% chance of success, and interested in 3 or fewer successes, apparently there's a 98% chance that you get 3 or fewer. 1 minus that gives you that 1.5% that it is more than 3, right? Not equal to. So ultimately, kind of sum this up. What you want to do for a binomial distribution, if you're going to find out binomial probability, is state the distribution and the values of interest. So if you're doing work for this, you need to state that you're dealing with a binomial distribution, what you're interested in, maybe define a random variable, and then define the number of trials, the probability of success, and make sure that those values are clearly identified. This is for constituting work. You can perform your calculations. You can either do the binomial probability formula that you find, or probably what you guys are going to end up liking more is binom CDF, PDF, and CDF. But you got to make sure that you define N and P, that you're dealing with a binomial distribution. And then ultimately come back and answer the question that was asked in the end.